Classification is where there's something you want to predict called the label or the predicted variable, and that something that you want to predict is categorical. The answer is one of a set of categories, possibly 0, 1, and not a number. In a previous class, we discussed several algorithms for classification, including step regression, logistic regression, and J48 or C4.5 decision trees. Today we're going to discuss more classification algorithms, starting with decision rules. Decision rules are sets of if-then rules which you check in order. So in other words, you check the first rule. If the first level is true, go with the answer. If it's not true, take all the rest of the data and consider that within the second rule. Within that second rule, if the answer is correct, go with that. But if the rule is not correct, then go on with the remaining data. So for example, if time is less than 4 and knowledge is greater than 0.55, then correct. So we take all the cases where time is less than 4 and knowledge is greater than 0.55. If they're correct, we're done. We take the remaining data and say, within that data, if time is less than 9 and knowledge is greater than 0.2, then we say correct. Now we take the remaining data and say, if num attempts is greater than 4 and knowledge is less than 0.33, then incorrect. And finally, we take the last part of the data and say, otherwise correct. So every time we operate a decision rule, we're taking part of the data and just saying, all right, we know the answer, taking the rest of the data and only considering among that. Like anything we discuss in this class, there are many algorithms for decision rules, and the differences between them are in terms of how the rules are generated and selected. The most popular subcategory, which includes the popular algorithms JRIP and PART, repeatedly creates decision trees, which we talked about a couple classes ago, and distills the best rules out of them. Decision rules are relatively conservative. In particular, they lead to simpler models than most decision trees. And decision trees, at least J48, are already a relatively conservative algorithm. They also lead to extremely interpretable models, which is a difference from most other data mining approaches. They're good when multi-level interactions are common, just like decision trees. Now let's talk about K-star. K-star is an instance-based classifier that predicts a data point from neighboring data points. It weights points more strongly if they're nearby. So let's take an example. Let's say that we have these data points with blue and red. And you can see that blue and red kind of each have a region, but there's not an easy way to say, oh yes, it's exactly this. Now let's say we need to classify a new point, the green point. To classify the green point, we look at every other point and its distance from the green point and weight in favor of the closer points. So you can see here that the circle, kind of a close circle around green, only has blue. As we get out a little further, we get some red. But compared to the initial blue set, we're still not all that much red. K-star is good when the data is very divergent, when there's not easy patterns but there are clumps. Lots of different processes can lead to the same result. And it's kind of intractable to find general rules. But data points that are similar to each other tend on the average to be from the same classification group, from the same class. A big advantage to K-star is that sometimes it works when nothing else works. My group in specific has found that it's useful for detecting some emotions from log files, where there's many different ways that emotions can manifest itself within a student behavior, and they may not be all that related. But the big drawback is to use this model, you need to have a whole data set, which makes it sort of intractable for use in a running educational system. If you imagine having to have 1.6 million data points that your system has to go through every time it wants to make a decision, that doesn't work too well. On the other hand, for kind of offline analysis and discovery of models analysis, it can be a very powerful tool. Now let's talk briefly about bag stumps. Bag stumps are related decision trees, where you create a lot of trees with only the first feature, and then you aggregate across them, something called ensembling. This is a relatively conservative algorithm because it just doesn't take very complex models. A close variant of this that's a little less conservative is random forest, where you build a lot of trees and then aggregate across the trees. A common thread in all these successful algorithms is that they're fairly conservative. They find relatively simple models compared to some other approaches, and because of that, they're not particularly prone to overfitting, where they fit to the noise in the data as well as the signal. These algorithms appear to do better for most educational data mining than less conservative, more aggressive algorithms. In brief, that's because educational data has a lot of systematic noise. Support vector machines are such an example. They conduct dimensionality reduction on data space and then fit a hyperplane which splits the classes. This creates very sophisticated models, and it's great for text mining for reasons that aren't worth going into right here. It's also great for sensor data. but it's not optimal for most other educational data, including things like logs, grades, and interactions within the software. Another complex algorithm is genetic algorithms, which use mutation, combination, and natural selection to search the space of potential models. They can produce inconsistent answers because they leverage randomness in their mutation and combination. They're a powerful algorithm for finding complex functions, and they work for a lot of problems, but in educational data they again tend to overfit a little. And a third one is neural networks. Neural networks compose extremely complex relationships through combining what are called perceptrons that can be combined in interesting and different fashions to fit very complex functions. They find very complicated models. Here's an example from Solar and Stevens, and what you can see is that it's got these 36 nodes, and in each node it's using a different weighting of the information. And each of these 36 nodes represents a different subset of the population. You can fit very complicated things in this, and it can be good for some educational problems. But in fact, the difficulty of interpreting nonlinear models like neural networks is so well known that they put a sign up about it in New York City. I'd like to make a quick note. Support vector machines, genetic algorithms, and neural networks are great for some problems. They're really fine algorithms. But for most types of educational data, they haven't historically produced the best solution. So when someone comes to you and says, "But you're not using a neural network. How can educational data miners not use neural networks? You must not have caught up to the 1970s. You can say, well, actually, lots of people have. It hasn't been published all that much because it kind of doesn't work very often, and people are kind of reluctant sometimes to publish the algorithms that don't work. But it's kind of a well-known piece of lore within the community that for most problems, and Stevens and Solar are an exception, they got some nice results there, but for most problems it hasn't been a very successful method. So in later lectures, I'm going to talk about goodness metrics for comparing classifiers, also about validating classifiers, and about classifier conservatism and overfitting in a little more detail.